Am I audible? Say yes or no. Okay. Let's start the today's session, right? So next we are going to discuss about. So actually, we are in comparator only. I think yesterday we had completed the operation of the comparator. At the end of this comparator only, right? We have left the class. Fine. Let's start from there. Actually, what we had been discussed in the last class, we saw the basic operation of the comparator. So usually that is comparator. I cannot say comparator. We are discussing about flash or parallel type of ADC, right? So flash in the sense one click you can receive the output. That's all, right? So it's required only one click. That is already. At the same time, we also observed, right? So we are going to vary the value of analog output voltage, that is sorry, input voltage. So with the help of this variable input voltage, we are what I can say turning on the comparators. That is, we are letting the comparators to produce one, such that one means high signal or electrical signal that will going to enable the correspondent logic gate behind of this priority encoder. That logic gate will produce what? It will count to the next value. It will produce the next binary equivalent value in the output side. Of course, we are discussing about what? Analog to digital converter. See there, I am having what? My input is analog only, but in the output side, we are receiving what? Digital with the help of some components. That's all, right? So this is all about basics of the comparator. In comparator, the number of that is conversion time of the parallel or flash type of ADC is T clock. Only T clock. You don't need to. It is not depending on the number of bits that we are going to observe here. It is not depending on the input voltage that we are going to keep, right? So the thing is what? It's simply one clock, right? It's only depending on output conversion time. It's only depending on what clock period that we are applying. That's all. There are no more things to discuss here, right? So the one thing I would like to finally conclude here, that is concluded here, the thing is in flash type of converter, right? You can, that is in case of flash or parallel type of ADC, it does not matter how many bits that we are going to consider, right? Clock or conversion time period of the flash type of converter is independent of the number of bits. Please make a notes because you'll be tested for some theoretical questions, right? Do remember. And the second thing I told you, the number of voltage divider or potential divider that we are using in the input side, that is called resistance. Number of resistance, simply we are calling that. The number of resistance, it will be the, what it will be represented, that is, or it can be calculated with the help of what? 2 power n, right? 2 power n. If number of bits are 2, then the total number of resistance that it should be required to design parallel or flash type of comparator is what? 4. Now when I am considering 3 bits, so here we took 3 bits, right? In 3 bits, how many resistors are there? 1 2 3 4 5 6 7 8. Totally we are getting 8. So 3 bits in the sense 2 power 3 will give you 8 resistors, right? So totally I mean of 8 potential divider. That is, your value will be equally divided, right? It will be equally divided, right? And it will be equally shared with all these people, right? Yeah. And next thing is number of comparators, right? So if you are designing what I can say 3-bit 3-bit parallel ADC, for 3-bit parallel ADC, how many comparators are required? 2 power 3 minus 1, such that 7 comparators are there, right? 1 2 3 4 5 6 7. Like if you are designing 4-bit parallel comparator, 4-bit parallel ADC, then the comparator is what? 2 power 4 minus 1. That is 2 power 4 means 16. 16 minus 1 should be equal to what? 15, right? So totally 15 comparators are required in order to design the what I can say 4-bit parallel or flash type of ADC. Clear? I hope things are very clear, right, to you all. Let us discuss about the final converter, right? That is called dual slope. I said that method is completely different from these things, right? I am repeating once again. Till now we had been discussed about counter type of ADC, and then we had been talked about successive approximation register ADC. Now we are discussing about parallel or flash type of ADC, right? In all these cases, from the input side, right, we saw the basic block diagram of our converters, right? So in the basic block diagram of our converters, usually what we are keeping, right? I mean need of when the moment we are injecting some what I can say practical signals, right? That practical signal might be what? It might be a temperature or pressure I said already, right? It might be a sound or velocity or speed, speed signal, whichever the things that you want, that is electrical signal, might be voltage, current, okay, whichever things that you want, you can just pass it. But if it is first of all, this given signal should be transformed into electrical. For that we are using anti-aliasing filter, sorry, transducer, right? So for that we are using what? Transducer. So what is the purpose of transducer? Transducer means it's a converting device, right? The device will convert the signal, whichever the signal that we are giving, that signal will be what? Converted into electrical signal. And then what we had been discussed about, we are discussing about anti-aliasing filter. Purpose of filter we know, right? Actually inside of this anti-aliasing filter we are discussing about what? Low pass filter. And then there is one more component that I had been inserted into the circuit, that is called the sample and holder, right? That's very very important, right? Sampling and holding process is very very important, right? So I told you, right, in all these type of counters, like all this type of ADC, like a counter, successive approximation register, and flash or parallel type of analog to digital converter, in beginning of this input side, actually I have not shown that circuit here. It does not mean that sample and hold circuits are not required for this back, right? In beginning of this one, right, so back side of the circuits, right, always we are trying to keep what? Sample and holding circuit. So the finalized conclusion is, at last we are going to design dual slope integrator, right? While designing the dual slope integrator at all, there is no need to discuss about the point is called sample and holding circuit, right? So that is not required. That circuit itself we can observe that one, right? So that's it's over completely. So sample and holding circuit does not required for whom? Dual slope integrator. But we know in the dual slope integrator accuracy is very high, right? You can get the exact data, accurate data. But the problem with the dual slope integrator is it is the very very what I can say slowest converter. We saw already, right? So yesterday when we are discussing about the speed conversions, right, who is working at very slow, right? Dual slope integrator only. But the another side is its advantage is, one side its accuracy is not good, its speed is not good, but another side it is the best device, right, for in the accuracy point of view, right? Dual slope integrator is the best device, right? Fine, let us start our operation. That is, finally we are going to discuss about dual slope integrator, right? So keep that in. So we are going to discuss about dual slope integrator. I told you in your free time should try to learn the basics of what I can say single slope, right? So single slope integrator, you can simply search it on Google. For that I'm not referring any books, right? Because just how to learn the basics. Why we are going up with the dual slope integrator? Already there is one more slope integrator is available, that is called the single slope integrator, right? There is some drawback. You please try and figure out those things, right? In your free time, what is single slope integrator? What is the what I can say operation of the single slope integrator? Why we are not using single slope integrator? Raise the questions and just to enhance your knowledge. That's enough. Okay. Let us design the last type of ADC, analog to digital converter, that is called what? Dual slope integrator, right? So we are going to discuss about dual slope integrator. Anyway, before going to discuss about the dual slope integrator, understanding the property of integrator is much important here, right? So that is, anyway, we are going to discuss about what? Dual slope integrator only, right? So there is no doubt. First, let us discuss. Let us see the meaning of this one, right? It means, what do you mean by dual? Dual means two, correct? Yes, of course. Slope means what? Slope means there might be a ramp signal you can observe. Either it might be like this, or it might be like this, or it might be like this. Clear? So that is called what? Slope. It is simply called slope, right? Okay. Next, what do you mean by integrator? Of course, we are going to use some devices. That device will going to do the action, that is, it will going to take the integration for the given function, right? So totally that is the general meaning, right? So we are going to create two slope integrator. Are you getting me? I am going to create two slope. Dual means we are going to create two slope integration, that is, with the help of integrator action we are going to create two slopes. That's all. There are no more things to understand from this sentence statement that I am giving, right? So let us continue our discussion from here. So first of all, I would like to talk about this integrator, because in mathematics we learn the basics, how to do the integrations at all, but we have to take the same action in our electrical devices. Now we are in electrical circuits, right? Now if I pass some signal through some devices, what the device has to do? Right, in the software side itself, the signal that you are passing through the device has to be integrated, right? So like that, I'm looking for a perfect integrator for my device. Let me draw the integrator equivalent circuit with the help of operational amplifier, right? So that is one of the application of the operational amplifier. Operational amplifier can do addition, subtraction, integration, differentiation, all things could be possible. That is the best version, right? That is the beauty of your operational amplifier. That's why it is called operational amplifier. It will going to do many action. It will amplify the signal, right? Buffer circuits can be possible, right? So everything could be possible, right? We will see, right? So anyway, the one of the application of your operation amplifier is simply called integrator. We are going to design the integrator circuit with the help of operational amplifier only, right? So first let us discuss about the basic property of your integrator. Later we will talk about dual slope. Slowly I will insert the elements, right? Okay, let us take integrator alone, right? So first our target is we are going to achieve the properties of integrator, right? Now integrator stands, right? So integrator means, let us take the operation amplifier. This is our op amp, right? Yeah, anyway, it has two terminals. One is inverting terminal, another one is non-inverting terminal, right? So let me give the input to this inverting terminal, and here I'm going to get some feedback, okay? And this is the point where we are going to receive the output, and let me connect it with the ground point, okay? And here this is the point where we are going to apply input value, right? You can call it as input voltage or reference voltage or analog voltage, right? So anyway, we are going to consider two voltages. Later we will see. First I'm considering some voltage here, that's all. This is some resistor. Here we are going to consider our capacitance, right? So C, capacitance C. Now I would like to obtain the output of this system. In order to obtain the output of the system, I would like to go ahead with the Laplace transformation, right? Now tell me, what is the Laplace of capacitor? Laplace of capacitor is 1 upon C into S. I hope you all remember, right? Anyway, Laplace of resistance will be again resistance, because it's a real element, kind of real element, right? Yeah. So let us start with the basic properties of the operation amplifier. Usually in operation amplifier, we are going to use the concept is called virtual grounding, right? Where we are going to apply virtual grounding subtle. I told you I will give clear-cut demonstration in analog electronics. Don't be panic, right? Just to learn the basics, right? According to the concept of virtual grounding, right, the value of V plus and the value of V minus are always equal, right? The value of V plus and the value of V minus are always equal. It means since we have zero voltage here, same zero voltage will going to appear here also, because both are equal. And second thing is, internally the op amp, right, the input resistance offered by the op amp is what ideally I am speaking, that is infinite, right? The internal resistance, input internal resistance offered by the ideal operation amplifier is infinite, such that current taken by these internal branches are going to be 0 ampere, which is always 0 ampere. There is no current entering into the operation amplifier in both these terminals, right? Fine. So let us apply once again nodal at this junction in order to obtain the solution for this given function, right? If you apply nodal, what will you get? Listen guys, actually I'm just taking them outside, right? See there, here we are having zero voltage, right? And here we are going to consider capacitor. Of course, its value is 1 upon CS. This is the point where we have output. This is the point where we have input, right? Now the thing is, see, there is one more branch. I know there is one more branch, but that branch is useless. It is consuming 0 ampere. We no need to worry about that branch. Right now, just to consider these two branch. According to nodal analysis, your selected node is the superior one, and that will going to deliver the current for your entire circuit, right? From this node, we are going to deliver the current. Let me call this one as I1. Let me call this one as I2, right? Let us slowly try and bring the answer for this function. The thing is, its answer is going to be, first step, apply KCL such that I1 plus I2 will become equal to 0. Second step, I1 can be written as 0, right? That is the potential difference between these 2 points, 0 minus output voltage V0 upon capacitance Laplace is 1 upon C into S. Of course, exactly that is correct, right? Now, whereas in the input side, what we are going to observe, 0 minus input voltage V in, and the resistance is going to be R. It will be equal to 0, right? Just to reduce this function, right? From this I can say, of course, in Laplace, V0 can be written as V0 of S, Vn can be written as Vn of S. We know that things, just I'm writing, that's all, right? If you want to write in terms of yes, you can write, nothing is going to be wrong. Yeah, so Laplace V0 of S can be written as further. Here we have 1 upon CS. Okay, let us keep 1 upon CS itself. If I'll pass this term to the right side, automatically it will become plus Vn of S upon R. Of course, that is true only. Now let us pass this 1 by CS to the right side, such that it is under minus also. So finally what we are going to get, the output voltage V0 will become, right, that will become what, 1 upon CS. Don't think too much. Actually, we are directly shifting this value what, towards right side. I have 1 by CS only. Appa inga pogumbodhu 1 by CS, right? Fine. So already what we have, there we are having Vn of S upon what I can suggest, that is R, right? And we have minus also. Now let us write one more thing. this function can be rewritten as, let me take minus 1 by RC outside, minus 1 by RC outside. Let us consider V in of S upon S. What is this? This is integrator, right? So if we are integrating V in with respect to dt, its Laplace, right? Integrated function of input is what? Its Laplace is what? That can be simply written as V in of S upon S. So when we are taking inverse Laplace for this function, of course we are in Laplace only, till now we are in Laplace, right? Assume initial is 0, right? So if I'll take inverse Laplace for this, then it is become V naught of t become minus 1 upon R into C. Of course that is correct, and this function can be replaced by integral of V in of t into dt. That's all, right? So what is the conclusion here? Yes, happily we can say the circuit that we are considering here is simply going to act as an integrator, right? And its output is what? Let me place it in a side, right? Or its output, right? So it's V naught of t. Its V naught of t is going to be minus 1 upon R into C, integral of, right, whichever the voltage that we are passing from the input side, right, that can be integrated with the, that is with the help of this given circuit. Clear? That's all. So this is the basic operation of your integrator, right? I hope things are very clear now. Let us continue our discussion, right? Next, what we are going to do? Yeah, so let us remove all these things, right? Coming back, we are not designing integrator, we are designing dual slope integrator, right? So that integrator will going to help us to create dual slope. That's what I want, right? That is what I'm looking for actually. Yeah, shall we design? Yeah, let's start our operation. Now I'm going to consider once again some integrator only. Okay, let us design slowly, right? The circuit that we are going to consider is integrator. It is an integrator only, right? And then now we know the equivalent circuit of the integrator, that is minus plus. Of course I am connecting it with the ground, and here negative feedback will be taken, right? Okay, fine. And this is going to be our capacitor, this is going to be our resistor, and this is the point where we are going to consider two voltages. One is input voltage. This is simply called analog input voltage, right? Because we are designing what? Analog to digital converter. So your input voltage is simply called analog voltage. Don't think too much. Who's this analog? Where is coming from? I have some input voltage. I would like to transform it into electrical domain. That's all, right? And here, actually, I'm going to use a single pole double throw switch once again because there is some purpose. And here, I'm going to use minus V reference. I'm going to consider one more person, that is called minus V reference, right? Anyway, let us continue. I have a switch here. Just observe that one, right? I'm having a switch here, right? Yeah. Let us continue our operation with this. Now, what is our next target? I'm just going to keep it with some, what I can say, comparator that we are going to use here, right? So it's simply we are going to consider some comparator, and actually this input will be given to the non-inverting terminal, whereas your inverting terminal is connected with the ground, right? Yeah, this is your comparator. This is your comparator, right? That's all. That is enough. Directly we can give it to the counter circuit, right? We can directly give it to the counter circuit, right? And your counter will going to count the data, right? So once again, this is going to be counter, and here we are going to consider start of conversion. SOC pin will be there. Of course, we are also considering end of conversion, right? EOC pin also will be available, right? And you can count the data that you want, right? So you can just increase the number of datas up to n, right? And then once you count the data, then that is called, right, the edge point is called overflow, right? நீங்க டேட்டாவை கவுண்ட் பண்ணி முடிச்சதுக்கு அப்புறம் என்ன ஆகும்? ஓவர்ஃப்ளோ ஆகும். If you are counting 0 to 7, then 8 will become overflow, right? So when we are overflowing the data, maximum counter முடிச்சதுக்கு அப்புறம் again what will happen? Your counter has to reset, right? So such that this pin will be directly connected to this one. I hope I am going with the correct. Yeah, that's perfect, right? So this is going to be overflow, right? And where we are going to receive the output, of course you can collect the data from here once again, right? You can collect the data from here. Yeah, there is no issues. Fine. And you can start from what? B0, B1, you can run up to Bn minus 1. So this is the point where we are going to receive our output. Yeah. Now let us try and understand the operation. There are no big things to understand. This is simply called a dual slope integrator. In this dual slope integrator, in the output side, we are going to get two slopes. Let's start our operation, right? So actually what we are going to do here, the thing is, this is the point is simply called output voltage V0, right? Now, what will happen? Case number 1, right? Case number 1, this is called analog input voltage, right? Actually, I said there's a switch, right? Dual pole, that is single pole double throw switch, right? So let me call it as single pole only, but double throw is there, right? So we are using single pole double throw switch here, such that what will happen, I can connect this switch either with this input voltage or either with the reference voltage, right? So case number one, this switch will be connected with the input, right? So let us connect this one with the input. Case number one, it will be connected here. Let us consider, right? It will be closed with your input voltage. Now what we are going to obtain in the output side, let us see the output of this one. This is the output point, right? So here we are going to receive the output as V naught is equal to, we know the operation, integrated, just now we saw, right? So it give you minus 1 upon R into C, integral value of input voltage is what? That is V naught, right? That is VA, sorry, analog voltage VA with respect to DT. Right now we are continuing this integration, or we are going to continuously apply this signal for a particular duration. The duration is simply defined as 0 to T1, 0 to T1. Now if you observe this integration carefully, now it can be rewritten as, I can reduce this function as minus 1 upon, let me call it as V01 for a purpose. Later you will understand why I am putting V01. So this is minus 1 upon R into C. And just you can take analog voltage outside, because we are going to do integration with respect to dt, right? Okay, if you are doing this integration, then this dt will become t, right? And limits are going from 0 to t1, such that its output will become minus analog voltage va upon r into c. Upper limit is t1, lower limit is 0. T1 minus 0 will be t1 only, right? So its output is going to be minus va times of t1 upon rc. So what we are doing here, nothing, just wait for a moment. So here what will happen, the thing is, when the moment you are connecting your input supply, that is input switch, with the analog voltage, automatically your integrator will start doing its function, will start its, and it is doing its operation, right? So during this operation, your capacitor is going to keep on charging. Your capacitor is going to keep on charging, right? So such that during this conversion, when your capacitor is allowed to charge, at the same time what happens in the output side, right? So in the output side, here we are receiving negative voltage. If you observe this one carefully, right, the voltage that I am receiving here, it is negative voltage, right? So we are receiving negative voltage. Carefully observe this point, right? Here we are receiving negative voltage. What about the available voltage at the positive terminal? This term, that is this circuit, is simply called a comparator. We all know this comparator will produce 1 or 0. That is the outputs of the comparator. Output of the comparator, either it might be 0 or it might be 1. It depends on the voltage that we are injecting across the inverting or the non-inverting terminal. Actually, across the inverting terminal, we are injecting negative voltage. Do you all agree with me? Yes. I am selecting a particular duration. In that particular duration, I am injecting negative voltage across the inverting terminal. If you are injecting negative voltage across the inverting terminal, now I am just making the comparison. The comparison is across the non-inverting terminal, we have 0 voltage. Do you all agree with me? Of course. And the next statement I would like to conclude here. We all know 0 is always much greater than negative voltages. Yes or no? Yes. You can keep any negative voltages here, but 0 is greater than negative voltage. It means I can say case number 1. In case number 1, V plus is greater than the value of V minus, because the available voltage across the non-inverting terminal is 0. Whereas in the inverting terminal, I have negative voltage. Okay, negative voltage is compare pannumbodhu, right? So V plus is greater than V minus. Automatically, comparator output will going to set as 1. So it will going to pass the signal to the counter. Counter will start its counting. That is what I can say startup operation, right? So it will start at counting what I can say n bit data, right? So if it is counting n bit data, then what will happen? Case number 1, right? From 0 to T1, I would like to draw the waveform for this. I think that portion is visible to you all. Let me check it by myself and then I will draw. Yeah. Now carefully observe here. What will happen? Now if you observe carefully, listen guys, this is my output voltage V01. I would like to draw the output waveform, right? Just I would like to draw the output waveform. If you want to draw the output waveform, first of all you have to understand one thing here, right? With respect to time period t, of course t is going to be positive. We are going to wait for 0 to t1, right? So let me consider a particular duration, 0 to t1. During this time period, I take, what is the integration period? We are going from 0 to t1. I am selecting a particular time period, right? What type of time period is? Slowly understand. Listen, in between, in the selected time period, output voltage is negative. First of all, see there guys, the voltage that we are injecting in the analog input side, just observe this all things, right? So this is I am injecting, this is the voltage that I am injecting here, right? So R and C values are fixed here, V also will be fixed here. So based on the time period, this is positive time period only, but your voltage will become negative because it will be multiplied by minus. Because of this, what will happen? See there, magnitude is negative, time period is positive. Magnitude is negative, time period is positive. So we are lying in the fourth quadrant. First conclusion. Voltage is negative, but time period is positive. We are lying in the fourth quadrant. First thing. And second conclusion, if you observe, I said VI is constant, RC also constant. So can I write like this? V01 is directly proportional to T1. T1 in the sense 0 to T1. Right, so it means it's clearly denotes it's a ramp type of signal. T means ramp signal, right? So T in x axis T increase பண்ண போறீங்க, y axis on T தான் depend பண்ணி இருக்கு அப்படினா, of course we are going to get ramp. Of course that is called slope, right? So now you are going to get one ramp signal in between the period 0 to T1. Right, I'm getting some ramp, but that is negative ramp. Why we are drawing like this? That is negative ramp. If it is positive ramp, then it will go like this, right? So that is negative ramp, right? Actually, what your counter will do, the thing is, when the moment we are considering negative voltage in the output of the integrator, this negative voltage will going to set its sent to the output of the comparator as 1, because in the comparator, if you are injecting negative voltage across the inverting terminal, in the non-inverting terminal we have 0 voltage. So 0 is greater than negative voltage, such that output of the comparator will going to be 1. It will push the counter to start its operation by enabling start of conversion point, right? So automatically your counter will start counting its point from 0 to 7. For an example, if you are considering 3 bits, it will continue its operation from 0 to 7. If you are considering n bits, it will start its counting from 0 0 0. It will run up to 2 power n minus 1, right? So the thing is, this is the time period where we are going to count the data, right? So in this given time period, right, how many there is data we are going to count, counter will count, right, up to 2 power n minus 1. That is the maximum number of bits, right? Counter is keep on counting until, right, the capacitors keep on allowed to charge here, and we are pushing the counter to count its operation. That is to count the data, such that the counter is starting 0 1 2 3 4 5 6 7. Yeah, I'm ending the counts. That is count operation, right? Once your counter will counts, right? So during the time period, see that this is the final point where your counter will going to count its maximum value. Then what we have to do? Again we have to reset the counter. Reset in the sense, you will have to get back to the starting point. Again you will have to start your operation from 0. Again you have to reach the maximum value. Again getting back to the starting point. Again start the operation. Again do it. Repeat the procedure. This process is being again and again repeated. So the conclusion is, anyway, from 0 to T1 your counter is counting. Your counter is allowed to counting its data, right? Such that your counter is keep on counting its data up to the maximum point, right? So the allowed duration is 0 to T1. Next, what we are going to do, right? The next thing is, again after reaching the maximum point, right, that is the correspondent time period. T1 அப்படிங்கிறது நம்ம calculate பண்றதா. Usually when the moment as a designer I have to check all these things, right? So what is the maximum time period taken by the counter to complete its count with the help of dual slope integrator? This is the point where your counter is counting, completing its counting exactly when it is reaching T equal to T1. Next, what we are going to do, again you will have to let the counter to reset, right? So that is the point. Once again, see, during this period your capacitors keep on charging. Yes or no? Yes. Now you will have to let your capacitor to discharge the data, right? Now the thing is, see there, when your counter is completing it's completing its counting, right, then overflow will occur. This overflow will pass a signal. Okay sir, I had stopped my, நான் வந்து கவுண்ட் பண்ணி முடிச்சிட்டேன் அப்படின்னு சொல்லிட்டு என்ன பண்ணோம் அப்படின்னா, it will send a message here. அப்போ என்ன ஆகும் அப்படின்னா, இப்போ இந்த மெசேஜ் வந்து நீங்கள் என்ன பண்ணணும், உள்ள பாஸ் பண்ணணும் இல்லையா? ஸோ அதுக்கு நீங்கள் என்ன பண்ணுறீங்க அப்படின்னா, ஆட்டோமேட்டிக்லி வாட் வில் ஹேப்பன், திஸ் ஸ்விட்ச் பொசிஷன் இஸ் ரீசேஞ்ச்டு. நவ் இட் வில் பி கனெக்டட் ஹியர். திஸ் ஸ்விட்ச் வில் பி புஷ்டு and it will be counted exactly after T1. We are replacing, that is what I can say, the position of the switch will be changed such that what will happen, this signal is entering into the circuit. Now see there, your new input voltage is going to be minus V reference, that is coming from overflow. This voltage will enter here. Automatically what will happen, let us discuss about this second part, right? So the first part here, output voltage that we are receiving here, we can say the slope will going to give us minus VA upon R into C with respect to time period T1, right? So this is the first slope that we are receiving here. Now second case, let us discuss about the second case. So let us remove these things now, right? Now immediately, now what we are going to inject, we are injecting the second voltage, that is simply called reference voltage, right? Now what that reference will going to do, again let us continue our operation. The thing is, we are injecting reference voltage, negative voltage now, so it is coming here. Once again, if you receive the output, if you are receiving the output of V02, let me call it as V02, what we are going to receive, again same formula we can use, because it is integrator, its output is going to be minus 1 upon R into C. Of course integral of input voltage is what? We are going to give minus V reference, right? So we are giving our input voltage as minus V reference, and the period is we are what we are standing at T1, right? So we are standing at T1. We are going to continue our operation up to T2, right? We are going to consider some cycle we are going to consider some number of cycles. See how to wait in order to reset the counter, right? So let's with respect to time period dt. Now what we are going to receive here, if you are completing this integration, right? If you are just completing this integration, guys, listen, just I am going to perform the take the action in between this duration only, or else you can do like this, right? You can just start, you can treat this is my starting point of the second half, right? This is the starting point of the second half, and I am running up to T2. You can also consider like this. There is no point of confusion here, right? So we are going to start. This is the starting point of the second operation, right? Yeah, and we are going to run up to what? T2, right? And that is we are going to take. That is we are going to wait for some cycle in order to reset the counter, because your counter is what? It is waiting. It is what I can say. For an example, 3-bit counter is waiting at 111. Right, it is reached. Now I will have to reset the counter, right? Such that it has to getting back to the starting state, right? So let us see what will happen. During this case, it is going to be once again minus into minus will become plus now. Yes, right? It is going to be plus, and here we are going to receive, that is V reference, yeah, and the data, right? So if you are integrating this one, see there, V reference upon R into C. Once again, dt will become T. Upper limit is T2, lower limit is 0. So T2 minus 0 will become what? Simply we can say that is V reference into T2 upon R into C. This is simply called V02, right? So during this point, your counter will allow to reset its data, right? It is going to resetting, right? So this is from 0 to T2. Again, from that is from this point to this point, we are letting the counter to do this operation. Whereas why I am putting the slope in the opposite direction? Because if your slope is running like this, then that is called positive slope. If your slope is running like this, then that is called what? Negative slope. When I was traveling along with the first case, I was getting negative slope. Now just observe, this is positive slope. Then where I have to start? I will have to start the ending point of the first slope. Your first slope had been what? It is terminated at this point. So your journey has to be from this point. Then you can travel towards what? In upward direction. Of course, we are positive. We are having positive slope now. So this is going to be V reference upon R into C only. There is no changes with respect to T2. We are running with this second slope. Clear? Yeah. This is all about what I can say dual slope integrator. How many slopes are there? Slope 1, slope 2. Totally we had been received 2 slopes. Clear? And what about the total output voltage? Right? Case number 1, we were receiving some output voltage. This is our output voltage. Case number 2, this is our output voltage. Now what is the net output voltage available in the integrator? Right, our net output voltage offered by the dual slope integrator, right? So let us discuss about the total output voltages at all. I hope I had given complete things regarding these circuits. Okay, let us see the theory part of this one, right? So let us discuss about the output, right? Output equations, and which are all the things that we are going to expect as the questions, right, from this area. That things we have to discuss now, right? Yeah. Let us see the overall output of the comparator. Fine. Now what is the net output? Let us consider the net output V0 of t can be considered as, that is the part 1 V01, part 2 it is going to be V02. V01 minus analog voltage VA, time period is T1 upon R into C integrator. Whereas V02, that is reference voltage upon R into C into time period is considered as T2. Right? Now let us extend our discussion. Of course, this is going to be V02. Now second time, see there guys, here we are going to consider some n cycle, right? This is the second half, right? So the first half your counter is counting. In the second half we are resetting the counter. Its corresponding number of cycle can be considered as n, because that is exactly we don't know that value, but we have to find, right? In the second state, what will happen? Counter has to reset, right? Fastly it has to reset. How many cycles it is taking to reset, right? How many cycles, right? So that we have to find. So let us see. That is caps n denotes the number of cycles that we are taking to reset the counter, right? And then what will happen? Finally, when we are touching this T2 part, once again your counter is reset. Completely your output voltage will become 0. Exactly at t is equal to T2. While reaching t equal to T2, what will happen? V0 of T2 will become 0, because see there, at this point your counter is reset. Totally on the thermostat normal state, right? So in order to know the relation between these two guys, I am selecting that point, right? So that is at t equal to T2, I can write V0 of T2 will going to be equal to 0. or otherwise just you can take this expression, we can write minus VA T1 upon R into C plus V reference upon R into C into T2 will become equal to 0. That is the point where your counter will going to stops. That is stops in the sense end of conversion is completely over, right? The counting that is first it is counting the data and then it is resetting the data, right? Everything, all operations is over here. Finally, just to reduce this expression, you are going to get analog voltage into VT1 upon R into C should be equal to minus, if you are passing this term to the right side, it will become minus R into C into T2. Minus minus getting cancelled, right? Is there any other terms? Of course, RC also getting cancelled out. So finally, what we are going to achieve here, the data, right? So I would like to know the T2, right? The period that we are starting, right? T2 அப்படிங்கிறது யாரு? 0 to, I was assuming this point is 0 and this is T2. Second point, initial stage, right? So second person initial, that is starting point, right? So T2 can be written as, I can write analog voltage VA upon reference voltage VRF, right? And we are going to consider the time period as T1. Clear? So this is the formula that we are standardly using to obtain the relation between T2 and T1, right? Whereas T1 அப்படிங்கிறது first time, right? So counter is taking some time to count the data, right? So to count this, see there, so T1 can be written as, right? So how many, for how long it is waiting, right? To complete 2 power n minus 1 times of data with the clock pulse, it is waiting in the first case. Whereas your second time T2, how long it is waiting to complete the n cycle with the T clock, right? So to complete this one, counter T2 is waiting here, right? So just is, that is the relation between T1 and T2. In case of T1, what I have done, I was counting 2 power n minus 1 data with the T clock, that is the total time period. In case of T2, I was counting n that is, I can say n cycle with the T clock, right? So that is T2, right? So now we know T1 and T2, let us substitute that things, right, into the equation such that what we are going to get, guys, proper, right? Because we are in the area where you can expect the question, right? So that is very important area, carefully observe all things, right? So I can replace T1 can be replaced by 2 power n minus 1 into T clock. Of course, T2 also can be replaced by n times of T clock, such that I can say T2 can be considered as n times of T clock, that is the number of cycle should be equal to, here we are going to consider analog voltage VA upon, this is going to be V reference, of course, into time period is T1, that can be replaced by 2 power n minus 1 times of T clock, right? I hope that portion is visible to you all. Anyway, let me check it by myself once. Is that portion is visible, guys? Please let me know. Wait. Yeah, exactly, right? We are touching the border. Fine. So this is the relation. Now from this, say T clock, we can cancel it. So I can say number of cycle n is equal to analog voltage or input voltage divided by reference voltage into 2 power n minus 1. Clear? So that is the relation between, that is how we are finding the number of cycle, right? I hope you all have understand what I am trying to conclude. Clear? So from this, now we can take the output voltage expression V0. So from this we can write, see there, for T1 now we know the relation, for T2 also we know the relation, right? So T1 can be replaced by 2 power n minus 1 times of T clock. Of course, T2 also can be replaced by what, n times of T clock, and we also know the relation, right? This n can also be replaced by what, VA by V reference. Okay, so let us reduce this expression here, right, with the known datas, right? So let me give some names for the what I can say circuits, that is equations. Let me treat this one as equation number 1, right? And let us consider this one as equation number 2, right? And let us consider this one as equation number 3. Okay, let me do this one. Either number equation number 3 எடுத்துக்கலாமா? This is equation number 3 and this is equation number 4 and this is equation number 5. Okay, yeah, let us reduce the expression further. Let me remove these things, substitute all the values that we what I can say learned so far. அதை எடுத்து வந்து அப்படியே இங்கே சப்ஸ்டியூட் பண்ணுங்க. என்ன வருதுன்னு பார்க்கலாமா? So the value of output voltage V0 of T can be further written as minus VA upon R into C. There is no doubt. T1 can be replaced by 2 power n minus 1 times of T clock. Exactly, that is correct. Plus V reference by RC. There is no changes. V reference by R into C. Of course, this is valid. And T2 can be replaced by n times of T clock. Right, that is, we are substituting equation number 3 and 4 in 1, right? You can write like this, right? Substitute equation number 3 and 4 in 1. That is what I am doing now. Okay, that is the first step. Now immediately in the second step, let me treat this one as equation number 6. This is equation number 6. Next, I am going to do one more thing. Keep your equation number 5 in equation number 6. Equation number 5 in equation number 6, right? So let us continue our operation. This is going to be equation number 6. This is equation number 5, right? So your output voltage, once again, it can be further written as, right, V naught of t, it can be further written as minus VA upon R into C into 2 power n minus 1 times of t clock. Of course, that is correct. Plus V reference, yeah, that is V reference upon R into C into n clock can be replaced by, according to equation number 5, this can be replaced by VA upon V reference, okay, into 2 power n minus 1. Exactly, that is correct, such that V reference is going to be cancelled finally, right? So if you are reducing this expression further, what we are going to get? We are going to get minus VA upon R into C into 2 power n minus 1 with the t clock, right? So there is a 2 power n minus 1 with the t clock, right? So just observe, right? Once again, we are going to receive VA upon R into C, right? And this can be written as what? 2 power n minus 1 into t clock, right? Now what is the difference between first equation and second equation? Do you have any? I think I left something, right? What is this? This is n, okay. 1 second. 2 power n minus 1. Did I left any terms here? This is 2 power n minus, yeah, t clock is this one, right? So I just thought it is missing. Okay, now what is the difference between these two guys? No, there is same. So it will become what? 0. So the relation that I took, that is correct. What I took at t equal to t2, right? At t equal to t2, my total data will become 0. That is what I have done, right? So we had been proved. That's all, right? Anyway, remembering these terms, that is all the equations are very, very important, right? So we can calculate the V naught of t with the help of this one also directly, right? And because the data will be given to you, right? In the direct V reference will be given, another voltage will be given, and will be tested with this equation, right? So don't forget these things, they are very important. Wait a minute. Yeah. So what we have done so far, that is we learned the basics of the, what I can say, dual slope integrator, right? Just keep whichever the things that I had been derived with you, right? Because while solving the problems, they are going to help us to get the answer, right, quickly, right? So all these terms are very, very important. Next, what we are going to do? So approximately we can say one thing here. The thing is your counter. Now what is the maximum conversion time taken by the counter, right? So that is the final step that we need to calculate here, right? So the maximum conversion time taken by the counter, maximum conversion time of the counter, right? So that is what we are going to learn, right? So if you observe, the maximum conversion time approximately can be written as, it is, see there, your counter is counting and resetting the data, right? So totally the maximum time of the counter can be approximately written as twice of 2 power n minus 1. Clear? That is the maximum possibility. It means counter will take 2 power n minus 1 times of t clock, right, to count, and then again it will take 2 power n minus 1 times of t clock to, what I can say, reset, right? So totally maximum expected conversion time in case of dual slope integrator is twice of 2 power n minus 1, right? So what is the conclusion here? The conclusion is, we can say, right, I already told you, right, like that is, wait a minute, simplest one, it can be done as twice of, I said approximately, you can also neglect that 1, right? So that is 2 power 2n, such that if you compress this function, this is going to be t max, right, its conversion time. See, because we know the relation, right? We can directly write n க்கு நமக்கு relation தெரியும், t1 க்கு நமக்கு relation தெரியும். You can directly add them, you will get the relation, right? There are no more things to discuss, right? Fine. So the maximum conversion time can be written as t1 plus t2 add பண்ணீங்கன்னா you are going to get the answer. For n we know the relation, for t1 also we know the relation, right? Fine. So you are going to get approximately, see there, 2 power 1 dot 2 power n, that can be written as 2 power n plus 1, right? If you want to neglect that 1 also, you can neglect, but I don't want to consider, right? Approximately it will be equal to this one only, right? If you want to consider that 1, you can consider. Anyway, just to do, remember this equation, I'm not proving it, I know, right? This is enough. So the maximum conversion time of the dual slope integrator is 2 power n plus 1 times of minus 1. That's all. There are no more things to discuss, right? Finally, what we learn? We learn the maximum conversion time. At the same time, we learn the basics, right? See, counting time of the converter is very important, and then number of cycle, right? So this formula, how we are finding this number of cycle, that is also very important, right? Because you will be tested in your examination with this data only. Clear? So this is all about dual slope integrator, right? Anyway, the beauty of the dual slope integrator is it is counting, its data is accurate, right? I told you already, right? Its data is accuracy, its accuracy is very very high, but the problem is it is taking, right? So the number of clock pulse, it will become what? Twice of n plus 1 minus 1. That is the drawback of here. Maximum conversion time, you can multiply by t clock. I forget to consider. Yeah, this is t clock. Okay, this is the maximum time period taken by the, what I can say, dual slope integrator, right? I hope things are very clear. That's all. There are no more things to discuss, right? It is over, right? So finally we have completed converter also, right? Yes, let us solve the problems in converters, right, to get the ideas how we are facing the questions, right, in your examination. So let me solve few more questions. So wait a minute, I will do it within a time. Okay, write down the question. The first question is, the resolution of 8-bit analog to digital converter is, right? The resolution of, right? The resolution of question is the resolution of an 8-bit, the resolution of an 8-bit analog to digital converter, the resolution of an 8-bit analog to digital converter is dash percentage, right? So is dash percentage. Okay, now let us see the solution for this one, right? Actually it's quite interesting, guys. The thing is, listen, already we have seen resolution equal to step size equal to 1 LSB, right? Anyway, the general formula we saw to find out the resolution, right? The answer for the resolution is, right, without percentage we can define like this. You can consider V reference upon 2 power n minus 1. I said, right? That is with the reference, we are not considering this one, right? If you are going up with the input voltage, right, of course the 2 power n minus 1 will appear, right? This is the general formula. But the thing is, suppose if they are defining the resolution in percentage, right? Percentage of resolution, if you are expected to find out the percentage of resolution, then you don't need to consider this input voltages at all. Just resolution in the sense how many step size that we are going to consider, right, in percentage. That's all. That is what we are trying to conclude, right? The percentage in the sense, see, in this case you don't need to apply, that is we are not considering input voltage, just to consider number of step sizes, right? Each and every step, how many, what is the percentage? Percentage means value should not required. Input voltage நீங்க எவ்வளவு apply பண்றீங்கன்னு தேவையில்ல. How many step size we are going to consider, that is percentage, right? Anyway, the question is what? The resolution of an 8-bit analog to digital converter in percentage. Just to consider the number of step size in percentage, right? So that is going to be what? 1 upon 2 power n is what? N denotes number of bits. So totally we are considering 8 bits, right? So 2 power 8 minus 1 into 100, right? So that is going to be what? That is 1 upon 2 power 8. I hope you all know that is 256 minus 1 into 100%, right? So it will be equal to what? 1 upon 255 into 100, right? Just to reduce this one and post your answer, right? One second, I am checking whether the option is given to this one. Yeah, it is given as 0.392%. You can just check it by yourself. I hope that is correct. Clear? If my answer is wrong, please post it in the comment section, right? That's all. So let us discuss about the second question. Yeah, let me rub this one first. I know this formula I had not given because at that time I cannot directly explain this one. That's why while solving the problem I thought of giving this one, right? This one. Just to make a note of it, right? See, unknowingly I took red marker. Again I am trouble. There is fine. So next we are going to discuss about second question. Write down the number of comparators, right? The number of comparators needed in a parallel conversion type, right? The question is the number of comparator, right? The number of comparator needed, right? The number of comparator needed, the number of comparator needed in a parallel conversion type, right? So in a parallel conversion type, right? So in a parallel conversion type, 8-bit analog to digital converter is parallel conversion type, 8-bit, right? Conversion type 8-bit analog to digital converter, 8-bit analog to digital converter is 8-bit analog to digital converter is. I hope option is not required for this question, because we have seen in ADC, that is in flash type or parallel, right? It is called what? Parallel, in the sense it indicates what we are discussing about, flash or parallel, right? That is analog to digital converter. We saw the formula to find out the number of comparators, right? The question is find out the number of comparator, right? So what we saw, the formula is to find out the number of comparator. We saw the general formula, right? So the general formula that we wrote there is it can be simply written as 2 power n minus 1, right? Whereas in our case n is clearly defined as 8, such that your answer is going to be 2 power 8 minus 1. It can be written as 256 minus 1, or the answer is going to be 255. So the total number of comparators are required to design the 8-bit analog to digital converter is what? 255. That's a drawback. You know one thing, your comparator or your flash or parallel type comparator is limited with the 3-bit data, right? It's limited with the 3-bit data, because in 3-bit data you can go ahead with the what? 7 comparator. Of course, that is what I can say, it is inexpensive. Of course, that is expensive only, but I can tolerate. Suppose again, if you are increasing the number of bits, if you are going up with the 4-bit, then totally 2 power 4 minus 1, 15 comparators should be required. If you are raising the number of bits, right, just by increasing the 1 bit, see the difference, right? Here we are facing only 7 comparators, but here we are facing what? 15 comparator. Again, if I am raising this one, then it is going to be what? 32 minus 1, that is 31 comparators should be required to design 5 bits. So the conclusion is, designing of the circuit will become highly complex. We cannot do. And the second thing is what? Though this comparator is acting as a fastest converter, right? So though this parallel or flash converter is working at a very fast, the drawback is that is what I can say, it is expensive. Circuit is highly expensive, and the second thing is designing is really what? Complicated, because we have seen the observations, right? I am taking a long time to design the circuit. That's a drawback, right? Already I told you, right? So the design is what? It will be limited to the 3 bits only. See there, how many comparators should be required? 255 comparators will have to implement to design just for 8-bit analog to digital converter, right? So anyway, that is the answer for this one, right? So let us continue with the third question. Let me rub this one. Yeah, the next question is, one second. Write down the question. In a dual slope integrating type digital voltmeter, right? So they are considering in a dual slope integrating digital type voltmeter in a dual slope, right? So in a dual slope integrating type digital voltmeter, in a dual slope integrating type digital voltmeter, in a dual slope integrating type digital voltmeter, in a dual slope integrating type of digital voltmeter, is first integration is carried out for 10 periods. Its first integration, right? Its first integration will be carried out, right? Will be carried out for 10 periods. Will be carried out for 10 periods, right? 10 periods of the supply frequency of 50 Hz. 10 periods of the supply frequency, right? So 10 periods of the supply frequency of 50 Hz, right? So 10 periods of the supply frequency of 50 Hz, exactly. Okay, next, if the reference voltage is if the reference voltage used as 2 voltage, if the reference voltage, right? So if the reference voltage, right, if the reference voltage used as 2 voltage, if the reference voltage used as 2 voltage, if the reference voltage used as 2 voltage, used is, right, sorry, I made mistake here actually, has is not possible there, yeah, that is 2 voltage. The total conversion time for the input voltage is the total conversion time, right? The total conversion time. They are not asking maximum conversion time. You are requested to find out the total conversion time. The total conversion time required. The total conversion time. The total conversion time for an input voltage 1 volt is the total conversion time for an input of 1 voltage is dash second. That's all. That is the question, right? So let's start our operation for the given question. Yeah, they are given 4 datas, that is 4 options, nearly 100 millivolt. So let us see. So in option A they said that is nearly 100 millivolt, nearly 100 millivolt in option A. Option B they said that is nearly 50 millivolt, nearly 50 millivolt. In option C they said nearly 25 millivolt. Sorry guys, that is milli, I forgot to consider, just to put a milli here. In option D they said 5 millivolt, right? So which is equal to 5 millivolt. That's all. Clear? So totally they are given 4 options. Let's try and figure out the answer for our question, right? Can you please do it? You please try, because just now we had been discussed about what I can say, dual slope integrator, right? So can anyone please figure out the answer for this question? I'm just expecting your answer only, right? Post it in the comment section. Just try, right? Because just now I had defined the formula to find out the answer for this function, right? Anyway, they had given one conclusion, right? So first integration la evlo period avanga eduthirukanga அப்படிங்கறத அவங்க clear-ஆ கொடுத்துட்டாங்க, right? So we can find out the, I hope we can find out the total conversion time easily, right, from this function, right? See, first of all, let me define what we saw in that dual slope integrator. Let me draw the waveform first. I think we took 2 periods, right? So let me draw this one, right? So in the first here, the total conversion time is going to be what? Let me call this one as T1. This period is, let me call this one as T2, right? So the total conversion time, TT, is, that is total conversion time, right? Which is equal to T1 plus T2, right? And we saw how to write this one. T1 can be written as 2 power n minus 1 times of T clock, exactly, that is correct, plus, and second data is given as T2 can be replaced by number of cycles n times of T clock, n times of T clock. Again we had observed one more thing, right? Now we have to estimate the value of n. N denotes number of cycle that we are taking in this second half, right? Now how will you find out the number of cycle? For that we again went up with the one more relation, that is we took the output voltage expression, right? In that output voltage expression what we saw, right? So wait a minute. We saw the output voltage V naught of T can be, it was written as minus analog voltage divided by R into C into T1 plus what I have done, second I took, that is reference voltage V reference divided by RC into T2, right? Just we had observed the relation by making T as T2. At T is equal to T2, what we saw, the net voltage will become 0, such that I can just equal it to 0, right? So the value of V naught of T2, just it will be equal to 0, right, at T is equal to T2. From that observation, what we had been observed, I wrote, that is VA into T1. What we saw, this will become V reference into T2. From this T2 I wrote, T2 can be written as VA upon V reference. I only given this, that is told these things, right, into, that is going to be T1, right? This VA is known as what? Input analog voltage. I am repeating once again, that is input analog voltage, that is given, right? Fine, let us continue our operation. T2 is equal to, now from this we know the relation. The relation is T2 can be replaced by n times of T clock, of course we know, and in the opposite side we can write VA divided by V reference. If you forget these things in your examination, that is how you have to derive, right? Yeah, that's why I am doing these things. In the right hand side, what we have, T1 can be replaced by what? 2 power n minus 1 into T clock, right? Of course, such that T clock getting cancelled, and we can define n is equal to VA by V reference as into 2 power n minus 1, right? So into 2 power n minus 1. So what is the finalized conclusion? So from this observation, let us continue, that is let us continue our discussion here. So it can be considered as 2 power n minus 1 times of t clock, right? Of course that is correct. Plus n will be replaced by va upon v reference, yeah, va upon v reference into 2 power n minus 1 times of t clock once again, right? Guys listen, I am replacing n can be replaced by va by v reference into 2 power n minus 1, n can be replaced by va by v reference into 2 power n minus 1. Already t clock is available here, I am just writing, don't think too much, right? We are not learning any new things. Okay, let us remove this portion anyway. What is our next task? Let us club them together, right? If you are just clubbing them together, then what we are going to observe, our observation is going to be, right? I said, see there, 2 power n minus 1, you can just approximate it as 2 what? 2 power n, because did you observe your options? They said nearly 100 millivoltage, nearly 50 millivoltage. It means they are not exactly expecting the actual value, right? So just because of considering this one, there is no, your data is not going to be what? It is not a significant value. It's simple one, right? So we can simply number of okay, that is also they are given, they are not given. Okay, I'm just approximating this one, 2 power n minus, that is for my simplification purpose, right? Okay, such that we can write like this, 2 power n times of t clock, right? 2 power n times of t clock plus again va upon v reference. I think that values are given, right? All values given, right? So anyway, let us complete t power n into t clock. So finally, if you take this 2 power n into t clock outside, it is become 1 plus analog voltage va upon v reference, exactly, right? Into outside it can be done as 2 power n into t clock, 2 power n into t clock. Clear? Now this is going to be your total conversion time. This is going to be your total conversion time. Let us substitute all the data that was given in the question, right? Let's figure out. Let me remove rest of all things. These things not required for us, right? Yeah. Next, let me collect all the data. What it was given in the question, right? Guys, listen. Analog voltage VA, right? And V reference. Let me consider analog voltage in the sense that is input voltage only. I am repeating again, right? So that is input voltage only. What is the value? This is the total conversion time for an input voltage. It was clearly given as 1 voltage. So this is 1 voltage, first data. Let us collect the second data, V reference. What is V reference here? The dual slope digital voltmeter first integration be carried out for V reference. V reference is how much? That is 2 voltage, right? So V reference equal to 2 voltage. That is over. Yeah. Now we know the value of VA, V reference. Now, did you observe one more thing? What is the 2 power n times of t clock, which is the approximated period that we are considering to count the what I can say total value? Do you observe our dual slope integrator will taking some period to count the data? That is simply called 2 power n minus 1, or of course I can say near answer only. Now 2 power n minus 1 can be approximated as 2 power n. So I can say this is simply called what? 2 power n times of t clock. Correct? So in this period only I am going to count the data, right? So this is the point where we are completely counting the data, right? So this is the first half. Anyway, the question is what? We have to achieve this one, 2 power n to t clock, right? So idu nam eppadi find pandradha? Is there any other data? This is the total time period. Actually 2 power n to t clock denotes the total counting that I made here, right? இப்போ பார்க்கலாமா? தி டியூவல் ஸ்லோப் இன்டெகிரேட்டர் டிஜிட்டல் வோல்ட்மீட்டர் இஸ் ஃபர்ஸ்ட் இன்டெகிரேஷன். அவங்களே கிளியராக சொல்லியிருக்காங்க பாருங்க. ஃபர்ஸ்ட் இன்டெகிரேஷன் த சென்ஸ் ஃபர்ஸ்ட் ஒன், ரைட்? ஃபர்ஸ்ட் இன்டெகிரேஷன் வில் பி கேரிட் அவுட் ஃபார் 10 periods. Oh, fine. So 10 periods only we are carrying, that is we're counting a time period. This is counting time period only, right? 10 periods of the supply frequency of 50 Hz. Total time periodல நம்ம வந்து எவ்வளவு பீரியடுக்கு வந்து டேட்டா வந்து கேரி பண்ணிருக்கோம் அப்படிங்கறத அவங்க கிளியரா டிஃபைன் பண்ணிட்டாங்க. Right? Are you getting me? So we are carrying the data for 10 periods out of 50, right? So it is clearly defined. So we can say like this, 2 power n times of t clock is the maximum period that we are taking to count the total data. Out of total is how much? 50 Hz. Instead of giving the data like this, they are given like this, right? So the thing is, we are considering the total value as what? Total frequency, and it will be given what? Its time period is 10, right? So we are considering 10 period to complete this data, right? So that is indirectly given as what in terms of 10 by 50, right? Total value is 50. I am repeating once again. Total is given as 50, and we are taking what? We are going to carry data only for 10 periods, right? So 10 periodly we are completing first integration. It means it is completing its whole data counting, right? So such that the total conversion time can be defined as what? Period upon frequency, right? So that will give you the value of what? Wait a minute. Sorry guys. Yeah, so we are going to consider, so this is a 10 by 50 will give you the what total conversion time, right? See there, what is the periods means we can define it since heads we are considering what, how many cycles we are taking, 10 cycles we are completing, right? So the 10 states, right? It's denotes 10 states that I am taking here, right? So 10 by 15 putting up, what will happen, what I can say, automatically it is become what, number of cycles per second only, right? So frequency will be defined as number of cycles per second. Here it is given as number of cycles, cycle get cancelled, automatically your value will be in seconds only, you don't need to be worry about this one, right? Yeah, anyway, if you cancel this one, it is going to be what, 1 upon 5, which will be equal to 0.2. Finally, what we got, 2 power under t clock, it's clearly defined as, which is equal to 2 power 2, sorry, 0.2. Let us substitute all the variables. So the total conversion time is going to be, right? So finally, the total conversion time is going to be 1 plus analog input voltage, right? So that is given as 1 voltage upon reference voltage is given as 2 voltage, that is 1 upon 2 into 0.2. So what is the correct answer? That will be equal to 1 plus 1 by 2 means 0.5. So 1 plus 0.5 will become 1.5, or we can say 3 by 2. So whichever the thing that you want, you can consider. That is 1.5 அப்படிங்கிறது 3 by 2 தானுங்க. Yes. So into we are going to consider 0.2. So 0.2 divided by 2 becomes 0.1. 0.1 into 3 will become 0.3, right? So that is the total time period. 0.3 seconds we are taking. That is the total conversion time of the dual slope integrator. Just observe. Clear? I hope things are clear. Option la irukka modalla. Total conversion time option la illaye. Please wait a second. I think I made some mistake. What I have done. Please wait a second. Oh, sorry guys. These options are not for this question, right? Please forgive me. This is for next question that I wrote here. Idu appadiye remove pannidunga. Your answer is 0.3 seconds only. Where is that one? This is the correct answer. See there. Idu enadhu? We are defining the answer in millivolt. But what is the question? That is wrong option, no? I am writing that one for next question. Yeah. Wait a minute. Okay, let us consider actually the question. Let me take next one also, right? And the option update vechkonga adutha question ku. Let me write down the question. Write down the question first. A 4-bit analog to digital converter is used to, right? A 4-bit analog to digital converter, right? A 4-bit analog to digital converter. A 4-bit analog to digital converter is used to digitize an analog signal, right? A 4-bit question is, sorry, a 10-bit, guys, sorry, forgive me, I don't know what I'm doing, sorry. A 10-bit analog to digital converter, 4-bit கிடையாது 10-bit, அதுக்கான I mean அது சேஞ்ச் பண்ணிக்கோங்க. A 10-bit analog to digital converter is used to, right, is used to digitize, right? Digitize is used to digitize an analog signal, digitize an analog signal, digitize an analog signal, digitize an analog signal in the 0 to 5 voltage range, right? Analog signal in the 0 to 5 voltage range, that is input voltage, right? 0 to 5 range. Okay, fine. The maximum peak to peak ripple voltage, right? The maximum, right? The maximum peak to peak, right? So the maximum peak to peak ripple voltage, the maximum peak to peak ripple voltage, right? Just observe the maximum peak to peak ripple voltage that can be allowed in the DC supply voltage, right? The maximum peak to peak ripple voltage that can be, right? So that can be allowed, right? So that can be allowed, right? That can be allowed in the DC supply voltage is, that can be allowed in the DC supply, that can be allowed in the DC supply voltage, in the DC supply voltage, that can be allowed in the DC supply voltage, DC supply voltage, that can be allowed in the DC supply voltage, right? And they are given the 4 options. That is the max, that is the given, right? Now what will you do? What will be your answer? Just what it was given in the data. just think, we learned some basics, right? We saw some நம்ம அந்த staircase ல வந்து data வந்து எப்படி convert பண்றோம் அப்படிங்கறத நம்ம ஏற்கனவே learn பண்ணிருக்கோம், right? See there, given it is analog to digital converter. See, at sometimes in the input side your voltage will be given in the range only, such that அப்போ voltage வந்து rangeல கொடுத்தாங்க அப்படினா you can write Vmax minus Vmin as your input voltage, Vmax minus Vmin as your input voltage, right? If your input voltage will be given in the range, right? If it is given like this, இப்போ இந்த மாதிரி கொடுத்திருந்தாங்க அப்படினா actually you can write input or analog input voltage, right? Because we are designing what, analog to digital converter only, it can be considered as the range Vmax minus Vmin, that's all, don't think too much. Okay, that is going to be your total input voltage, right? Fine. So let us consider. Anyway, so from here what, that is 0 to 5 means 5 minus 0 is 5 voltage, right? Next, the maximum peak to peak ripple voltage that can be allowed in the DC supply voltage, right? So இப்போ நீங்க DC supply voltage ல இருந்து maximum peak to peak எவ்வளவு voltage வந்து நீங்க allow பண்ணலாம், அது எப்படி நீங்க டிசைட் பண்ணுவீங்க? See, the maximum allowable voltage from the input side, peak to peak or null side, that is maximum voltage na peak to peak only, right? That range it is defined as peak to peak, right? Minimum to maximum. அது வந்து நீங்க எவ்வளவு வந்து allow பண்ணலாம் அப்படிங்கறத question, right? So that can be allowed, what I can say, ripple voltage that can be allowed in the DC supply voltage, that is the question, right? So அப்ப நம்ம maximum voltage வந்து allow பண்ணோம் அப்படினா இத வந்து நம்ம யார் கூட வச்சு டிஸ்கஸ் பண்ணோம் அப்படினா immediately we need to think. சர்க்யூட் குள்ள ஆக்சுவலா நம்ம என்ன நடக்க போகுது அப்படினா, when the moment நம்ம இன்புட் வோல்டேஜ் வந்து அப்ளை பண்ணும்போது immediately we need to think about the resolution, கரெக்ட்டா? yesterday we saw the basics, right? resolution தான் ஃபர்ஸ்ட் உங்க மைண்ட்ல வரும். resolution அப்படினா ஸ்டெப் சைஸ், எத்தனை staircase வந்து we are going to consider, how many staircase we are going to consider, we need to consider step size, or it is called 1 LSB, or it is called resolution. I am repeating once again, நீங்க ஸ்டெப் சைஸ் வச்சு தான் யோசிச்சு பார்க்கணும், right? how many step size that it should be required, right? so எத்தனை ஸ்டெப் சைஸ் நமக்கு தேவைப்படுதோ that will decide your level of the voltage, right? so step size வச்சு தான் நம்ம என்ன பண்ண முடியும். இன்புட்ல see நீங்க இங்க சிம்பிளா நீங்க இங்க ரெஜிஸ்டர் பண்ற டேட்டா எவ்வளோ 5 voltage, that is analog voltage, available voltage. உள்ள என்டர் ஆகும்போது அது ஸ்டெப் சைஸா கன்வெர்ட் ஆயிடும். அப்ப எவ்வளவு வோல்டேஜ் வந்து ஒவ்வொரு ஸ்டேர்கேஸ்ல நீங்க அலோவ் பண்ணிருக்கீங்க. each and every staircase is going to be treated as the input voltage. You have to think like that, right? because நம்ம என்ன பண்ண போறோம், டேட்டாவை டிஸ்ட்ரிபியூட் பண்ண போறோம். Are you getting me? It's like a money that we are investing in the mutual funds, right? so it will be spread into what, இது வந்து 10 half இல்ல 20 half split பண்ணி we are going to invest in some different companies, right? growing companies in India, like அப்ப நீங்க 10 இதுல வந்து இன்வெஸ்ட் பண்ண போறீங்க. but I would like to invest the same amount of that is investment, I would like to do same amount of investment in all what I can say companies, growing companies, right? so அப்ப நீங்க என்ன பண்றோம், with the help of brokerage, right, we are going to இருக்கிற amount வந்து நீங்க 10 break பண்ணிட்டு same amount, right, in each and every staircase we are going to invest the same amount, right? it means each and every step will carry same amount of voltage here, right? அதுதான் உங்களோட input voltage. now for an example, out of 10 company, ISRO is also one of my company. I would like to invest some money on ISRO because I am having some hope, right? ISRO கண்டிப்பா டெவலப் ஆகுற நம்பிக்கை எனக்கு இருக்கு. so I am investing some money, right, for that project. அப்ப நம்ம இன்வெஸ்ட் பண்ணிருக்க money, for them the input voltage is what, the staircase is what. நீங்க அந்த 10 நீங்க பிரேக் பண்ணி வச்சிருக்கீங்க இல்லையா, அந்த 10ல ஒரு amount, one part is going to be the input for the ISRO. that is your input voltage, right? so what is the conclusion here? we need to calculate the stair voltage, right? if they are talking maximum ripple to ripple voltage அப்படினா inside உள்ள என்டர் ஆனதுக்கு அப்புறம் சிஸ்டம்ல ஒவ்வொரு ஸ்டேர்கேஸ்ல நம்ம எவ்வளவு வோல்டேஜ் வந்து கொடுத்திருக்கோம், that is very important, right? so that things will be calculated with the help of what, resolution or step size, right? so let us conclude. maximum voltage decide பண்றது step size, or we can consider 1 LSB, or we can consider 1 resolution. least significant bit தான் வந்து என்ன பண்ணணும் அப்படினா maximum நீங்க எவ்வளவு voltage வந்து நீங்க allow பண்ணனும் அப்படிங்கறத டிசைட் பண்ணனும், right? that is the step size or width, right? so the step size or resolution, we can also consider this one as the resolution. we saw all things, right? so this can be generally defined as input voltage, right? Divided by we can consider that is 2 power n minus 1. clear? yeah, let's continue our journey with this. input voltage is how much? that is range, it is given in range. usually in analog to digital converter at all, இந்த இடத்துல ஸ்டேட்மென்ட் எப்படி கொடுத்திருப்பாங்க அப்படினா it can be written as Vmax minus Vmin only. நீங்க புக்ஸ்ல ரெஃபர் பண்ணீங்கன்னா அவங்க இப்படி தான் கொடுத்திருப்பாங்க. anyway I don't want to differentiate these things like that, that's why I have not written in this way. that's not a big deal, right? yeah, that is equal to what, 5 minus 0 is 5 voltage only upon 2 power n minus 1. n denotes the number of bits. totally we are going to consider 2 power 10, I think, which is equal to 1024. that's what my answer. I don't know am I correct or not, let me check it by myself. 1000, that is 2 power 10 in the sense that is going to be 1024 minus 1 is equal to 1023. see 5 by 1000, 1023 approximately 1000 only. அவங்க nearer answer தானே கேட்டிருக்காங்க. so see there we can directly say 1023 nearer answer அப்படின்னா you can just approximate it, right? So it will be approximately equal to 1000 voltage only. 1023 it just approximated. Nearer answer 23 அப்படிங்கிறது 1000 க்கு பக்கத்துல தான இருக்கு. So we can just approximate it as our approximated answer is going to be equal to 5 upon 1000, or I can say it will be equal to what? 5 millivoltage. Correct? Directly we can say. Fine. Which is our answer? Option D. Clear? Fine. So let us take the next one. Once again, you are requested to find out the number of comparison carried out by the 4-bit flash type analog to digital converter. Of course, they are asking number of comparators, right? You know how to do. Anyway, that question is the way that we are approaching the question is different. Let me give you the statement, right? You have to understand. Wait a minute. Next we have to understand. That is the first write down the question, you please. The number of comparisons carried out, right? The number of comparison carried out. The number of comparison carried out in a 4-bit flash type of analog to digital converter. In a 4-bit flash type, in a 4-bit flash type analog to digital converter is. The question is what? Number of comparison carried out. It means the number of comparison, it depends on what? Number of comparator தான் இங்க comparison பண்ண போதோ. So number of comparison carried out in the sense indirectly they are asking you to find out the number of comparator only. எத்தனை comparison நீங்க carried out பண்ண போறீங்க அப்படின்னா it depends on the number of comparator. How many comparators should be required? 2 power 4 minus 1. Correct? That is 2 power n minus 1. General formula. So 2 power 4, 16 minus 1. So totally we are going to do 15 comparison. Correct? Yeah. Fine. So let us discuss about the next data. One second. Yes, wait a minute. I'm just looking for the questions only. Yeah, first write down the question. A dual slope analog to digital converter, right? Again, the question is a dual slope analog to digital converter. 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 Right, a dual slope analog to digital converter uses an n-bit counter, right? Uses an n-bit counter, right? Uses an n-bit counter. When the input signal VA is being integrated, uses an n-bit counter. When the input signal VA is being integrated, right? Is being integrated. When the input signal VA is being integrated, the counter is allowed to count up to the value, right? The counter is allowed to count, right? The counter is allowed to what I am doing, the counter is allowed to count up to the value, right? Up to the value, right? The counter is allowed to count up to the value is dash, right? And they are given 4 options. Option A, 2 power n minus 2. Option B, they told that is 2 power n minus 1. 2 power n minus 1. In option C, they said that is VA, that is equal to VA only. In option D, guys listen, they have not written like this. Actually, that statement is given as which is proportional to VA, right? Proportional to VA, right? And they said inversely proportional to VA, right? Next they said inversely proportional, that is inversely proportional to VA. That's all. That is proportional to VA, and that is inversely proportional to VA, right? Now, what is the question? The dual slope analog to digital conversion uses an n-bit counter. இது வந்து n-bit counter யூஸ் பண்ணிட்டு இருக்காங்க, right? So when the input signal VA is being integrated, right? நீங்க input signal integrate பண்ணிட்டு இருக்கும்போது the counter is allowed to count up to the value, right? Can you please post your answer? I'm just expecting you to drop your answer here. Please post your answer now. Wait a minute. Total counting, which is proportional to what? You are requested to post your answer, right? So the total counting is what, which is proportional to dual slope integrator converter is used to count what? N-bit counter on the, that is, it is acting as an N-bit counter when the input signal VA is being integrated. நீங்க input voltage வந்து integrate பண்ணிட்டு இருக்கும்போது the counter is allowed to count the value up to what? When we are doing integration with the help of this counter. Why are you guys are waiting? I don't know, right? See then, actually what is the question? Given it is dual slope analog to digital converter once again, right? So in dual slope analog to digital converter, the total counting that we are going to count here, right? Anyway, first your counter is going to count what? Up to t1 we are counting 2 power n minus 1 times of t clock. Again what will happen? Your counter is allowed to count up to, right? So again what will happen after this is the maximum count. Anyway, it is not stopping. Again we have to, it has to recount, right? Again it will going to consider some n cycle, right? If you are taking the total counting time period, already we had been observed, right? So here n denotes what is the relation. We saw in the first cycle we are going to consider 2 power n minus 1 times of t clock. Of course, in the second counting period we are going to consider n into t clock, that is the total counting, right? That is the total counting cycle, number of cycles that we are taking, right, to reset the counter, right? And we have seen the observations, right? What we saw, this can be defined as t1, of course, and this can be defined as what I can say t2, right? Now the question is, the counter is allowed to count up to, right? நீங்க maximum எவ்வளோ counting வந்து நீங்க proceed பண்ணுவீங்க? See guys, actually they left some word, right? According to the given data, we should just go with this one only, right? Counter வந்து எவ்வளோ data allow பண்ணோம் அப்படின்னா that's all. This is 2 power n minus 1 only. Directly you can post your answer. I don't know why I am doing this much of things. Actually the question is what? The counter is allowed to count, right? Count up to maximum எவ்வளோ வரை count பண்ணும்? For n bit counter it is allowed to count up to what? 2 power n minus 1 data only. That's all. If you are requested to find out the number of cycle, right? So number of cycle, sorry, this is number of cycle, then that can be considered as n. I'm just my mind is blowing with that one, right? So if it is, if you are requested to find out the number of cycle, then what will you do? Number of cycle if you are requested to find, then your answer is what? We saw already, this can be written as analog voltage upon reference voltage, right? That is VA by V reference into, we can consider, right? So this is the time period, that is I brought the relation already, that is 2 power n minus 1 into t clock, right? So that anyway, we just, this is the relation between these two guys, right? If you are requested to find out the number of cycle, here the relation is, anyway V reference is fixed, we are not going to touch that one. Number of bits is fixed, so we can say the number of cycle is directly proportional to analog voltage or input analog voltage. In this case, the number of cycle are this one, right? So this number of cycle is directly proportional to what? It is going to be VA, analog voltage VA, right? It depends on the question that they are asking here, and according to the given statement, your counter is allowed to count up to what? 2 power n minus 1, and then what will happen? Again it will count. This is number of cycle it is taking to recount, right? So the number of cycle ketana, that is proportional to VA. Number of counting ketana, that is 2 power n minus 1 only, right? Sorry, forgive me, I am taking too much time for this one. My mind is blowing with another concept. Yeah, so let us consider the next question. Let us take wait a minute. Question number, yeah, among the following four converters, these among the following four converters, write down the question. So let me write. Yeah, among the following four converters, question is among the following, right? Among the following 4 converter, among the following 4 converter, among the following 4 converter, the slowest ADC, right? The question is the slowest, right? The slowest ADC, the slowest analog to digital converter is dash, right? And they are given 4 options for this. Option A, they said parallel. We all know there is one more name for this parallel, that is called what? It is also called flash type of converter. And in option B, they told that is successive approximation register, successive approximation register. Option C, given it as integrating type, given it as integrating type, that is they are talking about dual slope. In option D, that is going to be counting type, they are talking about counter. Which is the correct answer here? Of course, we know the relations between the conversion time of these 4 people, right? So let us see, while discussing about parallel or flash type of converter, the total conversion time can be simply considered as what? It will be equal to T clock only, that's all. Now, while discussing about successive approximation register, the total conversion time can be simply written as n times of T clock, where n denotes the number of bits that we are considering. While discussing about integrated, the approximated conversion time can be written as 2 power n plus 1 minus 1. That is the maximum conversion time. While discussing about counter type, right, that value is considered as 2 power n minus 1 times of T clock, correct? That is the total conversion time. If we compare all these things, which is the fastest one? The fast one is what? Parallel comparator. And then this is the priority will be given. This is the first one. Second one is what? Of course, successive approximation register is going to be the second one. Third one is what? Counter is going to be the third person, right? Working at very fast. Last we are going to consider. Priority will be given for this one. This is the order that things we saw. Anyway, question is what? Among the following converter, which is the slowest analog to digital converter? Slowest, fast means this one, slow means what? Integrating type, right? So your answer is what? This one. Fastest அப்படினு கேட்டிருந்தாங்கன்னா this one. Clear? That's all. Yeah, 1 second. Please wait a minute, this guy. I'm collecting the questions. Yeah. Next, the question is: the voltage comparator shown in the figure can be used in. It can be used as. That's all. Right? It can be used as. The question is given as: the voltage comparator shown in the figure can be used as. The voltage comparator shown in the figure. This is the comparator that they are given. The voltage comparator they are treating, that is in non-inverting terminal, inverting terminal, V1, V2. They are given 2 voltages. Of course, this is going to be output, right? The question is: the voltage comparator shown in the figure can be treated as. They said there are 4 options they are given. One is 1 bit quantizer. It can be act as a 1 bit, right? This is first cases, that is 1 bit, right? Quantizer, right? So this can be, it will act as a 1 bit quantizer. Listen, 1 bit quantizer. And option B, they said a 4 bit quantizer. It is 2 bit, right? It is 2 bit quantizer. In option C, it will act as a 4 bit quantizer. 4 bit quantizer. Option D, it will act as a 8 bit quantizer. It will act as a 8 bit quantizer, right? So can you please post your answer? It is very simple question. 1 second, I don't know where yeah, it's here. Now can you please tell me your answer? Post your answer, please. What is the property of comparator? Anyway, given it is what? Of course, it is comparator. We know the operation of the comparator. What type of operation that we are observing here? In your comparator, usually there are 2 operations. One is when the value of V2, right, will become, or let me go ahead with the V1. V1 is going to be greater than the value of V2. It means the voltage across the non-inverting terminal will become greater than the value of voltage across the inverting terminal. If V1 will become greater than V2, automatically it stands, right? It will set the output value as 0. Correct? How many bits are there? Only 1 bit. Binary data, right? Digital data. So we can say second case, Suppose if the value of V1 will become less than V2, then what will happen? Again we can say it will set the output value as what? V0 is equal to 1 only, right? Am I entering 4 bits or 5 bits or 6 bits here? No. The purpose of the comparator is it will acting as a what? It will just producing some clocks, right? That clock value, its output might be 0 or 1, but it is always what? How many bits are there? Only 1 bit. So it will act as a what? 1 bit quantizer. So what is the answer? The answer is option A. Simple question. Just they are testing your basic knowledge. That's all. Why no one posting your answers in the comment section? உங்களால் போட முடியலையா என்ன? Fine. So let us see. Let me select the next question. Write down a digital to analog converter, right? So let me remove this one. A digital to analog converter with a full scale output voltage. A digital to analog converter. A digital to analog converter. A digital to analog converter. A digital to analog converter with a full scale output voltage of a digital to analog converter with a full scale, right? So with a full scale output voltage of, right, a digital to analog converter with a full scale output voltage of, right, a digital to analog converter with a full scale output voltage of 3.5 voltage, right? Output voltage of 3.5 volt has a resolution close to 14 millivolts, right? Has a resolution close to, right? So has a resolution close to 14 millivolt. Yeah, 14 millivolt, right? 14 millivolt. Now the question is, its bit size is dash. Its bits size is dash. Its bits size is dash. I hope you all have remember. I had given the basic relation for this, right? In a relation, just to recollect the data that I had given. Wait a minute. The question is what? You are requested to find out the number of bits only, no? Wait a minute. Yeah. See what we saw, the digital to analog converter already we had been observed. This is full scale output voltage. It can be, in short, it can be written as FSO voltage, and it is given. This value is 3.5, and they had given the resolution. Resolution is how much? 14 millivolts. Now the question is what? You are requested to find out the bit size. Bit size means number of bits. N equal to what? That is the question. Can you please find your answer? Right, let us see. Actually, yesterday we had been observed something, right? When I was talking about full scale output voltage, right? Full scale output voltage. First, I have written this full scale output voltage as 2 power n minus 1 into input analog voltage Vn upon 2 power n. Just revise your notes. This is the first step that we had been observed from the staircase output. Clear? And then what I have done, I had been reduced to this expression as 2 power n minus 1. Okay, that is correct only. But input voltage upon 2 power n, it's so far it is simply considered as a step size or resolution or 1 LSB, right? We know all these things, right? So it can be replaced by a step size. Do you all agree with me? Of course, instead of considering step size, you can also consider what? Resolution. That is also correct, right? So we can also consider 2 power n minus 1 times of resolution. Is there any mistake in my conclusion? No, of course it is resolution. From this, what we can say, right? So let me write 2 power n minus 1 can be written as full scale output voltage FSO upon resolution. Any mistake in my conclusion? No. Let us consider full scale output voltage. It was clearly given as 3.5 voltage upon resolution also given, that is 14 millivolt. 14 milli can be considered as 10 power minus 3, such that I can reduce this function as it can be considered as 3500 upon 14. Guys, I just brought this 10 power minus 3 to the numerator. It will become 10 power plus 3. That is known as 1000. So 3.5 into 1000 is going to be what? 3500 only upon 14. Clear? That is the value of 2 power n minus 1. Let us reduce this function. From this, I can say it can be further written as 2 power n, which will be equal to 3500 upon 14 minus 1. Correct? Of course, that is the exact data. Now I am in need of number of bits. If you want to know the number of bits, then just take log on both sides with the base 2, such that log base 2, that is this value is what, 2 power n, and here also we are going to consider log base 2 with the data of, just take your calculation and proceed by the 3500 upon 14 minus 1. Now anyway this 2 getting cancelled out, so n will come out, it will be equal to log of 2, right, that is base 2 into what I have done, 3500, right. So 3500, you please just reduce this function, right. Now let me generalize some things here. This something is full scale voltage upon resolution minus 1, right. So we can write like this, full scale voltage upon resolution minus 1 will give you approximately, you can neglect this minus 1. I am repeating once again, you are getting, your answer is getting close, just you can neglect this minus 1, but I am giving exact relation. This is the formula to find out the value of, at sometimes you might be tested with some theoretical question, what is the relation between full scale voltage resolution and the number of bits. Just remember, right, this is the first time I am also facing these things, right. Okay, first, because this is a new question for me, just to solve it, take your calculation and post your answer. Otherwise anyway, let me do it by myself also, and then we will check out the answer, right. Yeah, it is going to be what, 3500, wait a minute, 3500 upon 14, yeah, 14. Of course I'm getting 250, 1 is very less when we are comparing it with the 250, so 249 we are going to take log base 2. Yes, of course I'm having, that is 7.96, I'm getting n is equal to 7.96, which is what, it is approximately equal to 8 bits, right. One second, let me check the options also. I think option is given. If it is, yeah, question number 4, wait a minute, let me check it. Of course answer is correct, right. So our answer is, they are given 4 options. Okay, answer is what, option B. That's all. That is how we are solving the questions, right. See, just to do, remember the basics, I am repeating, questions are very easy, right. You will be always tested with some chilly questions only, right, trust me. Fine. Remaining questions are same. Okay, let us take the next one. The next question is, write down, an 8-bit unipolar successive approximation register and 8-bit unipolar successive approximation register type ADC, we know that is analog to digital converter only, type ADC is used to convert, which is used to convert 3.5 voltage, which is used to convert 3.5 voltage to the digital equivalent output, 3.5 voltage to the digital equivalent output, right, to the digital equivalent output, yeah, that's fine, to the digital equivalent output. The reference voltage is 5 voltage, given it is, the reference voltage is 5 voltage, the reference voltage is 5 volt, the output of the ADC at the end of third clock pulse, right. The question is, the output of the output of the ADC, at the end of, right, at the end of the output of an ADC, the output of the ADC at the end of third clock pulse after the start of conversion, right, end of third clock pulse after the start of conversion, after the start of conversion, right. So after the start of conversion, that is the given question. Of course they are given 4 options. Let me register options also. 10 10 40, they said, In option B, given it is 1 000 40. Option C, given it is 40 40 000 1. Option D, 40 40 0011. Okay, they are given 4 options. Shall we pick? Yes, we know how to perform the operation with the what I can say successive approximation register, right? Our target is we have to achieve the equivalent value, right? So what we need to do, actually they are given 8-bit unipolar. Okay, everything is perfect, successive approximation register. But now the given it is, right, it is used to convert 3.5 voltage, right? It is used to convert the 3.5 voltage which is the that is digital equivalent output, right? Whereas what they are given, the given it is reference voltage also given. Reference voltage is 5 voltage, right? Now the output of the analog to digital converter, we have to treat this one as your reference voltage, of course. And the question is, at the end of the third clock pulse, what will be your answer? That is the answer that I am expecting your side, right? Because we have seen the operation, but the reference voltage also given. Now can you please anyone post your answer? Why are you not posting your answer? Any problem? Till now no one of you had posted your answer in the comment section. Why? What's wrong with you all? Please post your answer. One second. Where is that question? Yeah. Post your answer. No, na? I think there is some problem in the comment section. Okay, there is no issues. Let me try to bring the answer. Fine. Oh, sorry guys, I'm having some fishing. Yeah, fine. Let us start. Actually what it was given, 8 polar is given, 3 voltage. See, the conclusion is here, reference voltage also given. Now நம்ம last case la enna paathiruppona, directly we took the input voltage and in the successive approximation register just we found the decimal equivalent and just we made the comparison, right? So let us see the decimal equivalent. Actually in this case what we need to do, let us take the circuit once again, right, for your understanding. But while solving the problem in your examination, don't draw this diagram at all, because that will waste your time, right? So that is not required. For your understanding, I'm going to do this one here, right? So let me consider this is going to be our decimal equivalent, of course, and this is the point where we are going to consider our input voltage. Now the input voltage is we used to convert 3.5 voltage only, right? So we are going to consider input voltage is clearly given as 3.5 voltage, right? So just to keep your calci with you, right, let us start our operation. That is plus minus, that is comparator. Of course here we are going to consider our what I can say AND gate with the clock pulse, right? This is clock pulse. I said that value is going to be 1 only, right? So we don't need to worry about this one. That is, I hope I told you there is some control circuits will be there, that's all, right? It is not necessary that you have to keep this one. Anyway, this is going to be successive approximation register. Here we have 2 pins, startup conversion, end of conversion. Fine. Actually if it is given in the mari circuit kudukala appadina, they will give you a control circuit and they will put a clock here separately, and they said this is called what? Controlled circuit. This is called control circuit. They won't show these things at all. Fine. Anyway, let us see the operations. How many bits we are going to consider? 8 bits. So totally we need to consider 8 lines, right? So we are designing 8-bit converter. So 1 2 3 4 5 6 7 8, right? That's all. Next what we need to do, we have to convert this value digital to analog, and then we are going to pass it to the, that is the decimal equivalent. That's all, right? Let us see how to transform this value. Now here what it was given, in our case it is clearly given as, okay, clock pulse and all we will consider later. Input voltage is given as 3.5. You might be wonder, sir, 8-bit data நம்ம convert பண்ணோம் அப்படினா we are going to get some 128 number 128 இல்ல values வந்து என்ன வரும்? See, let us see. Actually 8-bit data அப்படினா successive approximation register ஓட first output என்னங்க? Let me write. This is the point where we are going to receive the output. Of course, the first output I said in the MSB you should set this value as 1, last bit inga, right? 8 bits abdina first consider 8 bits. Yeah, this is 8-bit data. First data is what? It is 1, right? So first thing enter ஆக போற data வந்து 1000 with 40. That is what it will enter here, right? If you observe its output is going to be what? இதோட decimal equivalent நீங்க calculate பண்ணீங்க அப்படின்னா, how will you transform it into its corresponding decimal equivalent? Its decimal equivalent is going to be 2 power 0. Guys, listen, how to transform the data from binary to decimal? You know how to do, right? 0 into 2 power 0, again 0 into 2 power 1, 0 into 2 power 2, plus 0 into 2 power 3, plus 0 into 2 power 4, plus 0 into 2 power 5, plus 0 into 2 power 6, plus 0 into 2 power 7. That is how we are transforming, right? So anyway, if you are putting, if remaining எல்லா வேல்யூமே 0, only one value has 1, so its decimal equivalent is 1 into 2 power 7, correct? That is how we are converting the data from binary to decimal equivalent. We saw the number conversions, right? That is 1 into 2 power 7, which is equal to what? 2 power 7. I hope that will be equal to 128 only, right? Yeah, so here I am receiving output la namakku ipo decimal equivalent evlo varudhu appadina 128. See there, this voltage is very large, whereas what it was given to us, given it is only what? 3.5 voltage. So what we need to do, so in this case decimal equivalent dhaan ungalku kedachirukka, you will have to transform it, right? appo neenga idha vandu enna neenga transform pannu appadina, you will have to transform this one as what? Equivalent decimal value neenga idha kondu pona appadina resolution use panni step size ku kondu ponum, right? Suppose if I will multiply it by, right, 2 power n, right? See, let me do one thing, just multiply it by resolution, right? I'm just multiplying it by resolution, right? அப்ப நீங்க இந்த resolutionால மல்டிப்ளை பண்ணீங்க அப்படினா, let us see, that is decimal equivalent VD, right? And what we are going to consider here, let me generalize the formula. This is going to be decimal equivalent, right? So decimal equivalent, if it is given reference voltage கொடுத்திருந்தானா, that is your options, right? Decimal equivalent, and you can just multiply it by what I can say resolution that will be given to you. You have to estimate the value of resolution also. Slowly understand, don't reference voltage கொடுத்திருந்தானா, this is the procedure, right? Now we know how to calculate a resolution. If reference voltage is given, then V reference upon 2 power n is going to be the formula to find out the resolution, right? Of course, in precise we can write 2 power n minus 1, right? So we can say V reference is given as 5 voltage upon data is given as 8-bit data. 2 power 8 is 256 minus 1 is going to be 255. If you are multiplying it by its corresponding resolution with the decimal equivalent, automatically it will be transformed into what? Equivalent output voltage. Are you getting me? See, in analog to digital converter, usually, see, this is digital to analog converter. Digital to analog converter la output voltage ku nama enna formula paathum? In case of digital to analog converter, output voltage can be simply written as gain of the operation amplifier into, and we saw decimal equivalent, right? I only wrote these things, decimal equivalent into resolution, correct? That is the formula that we are using. That is what I am doing here. Here a gain is 1, here a gain is 1. General formula, right? Anyway, for simple data without reference at all, we saw the operations, we saw directly without considering these things. But now reference voltage is given, we need to make the comparisons, right? So under this condition, write down the general formula. The general formula of the, what I can say, digital to analog converter is, in analog output of the digital converter is what? Digital to analog output is what? Decimal equivalent into resolution into what? 1. That is the correct option, right? So now you can transform. So decimal equivalent is what? 128. Now you can simply do the operation, right? So this is going to be 128. First clock la neenga kudukumbodhu, we are receiving 128 into resolution is reference voltage upon 255. You please do the conversion. Don't forget this procedure that I am giving here, right? If reference voltage will be given, then this is the way that you have to approach, right? Don't think too much. We know the output voltage expression for digital to analog converter. Just write down the output expression here, right? They won't talk about gain. If it is given, you can consider, but they won't give. Don't be panic. Gain won't be given. Resolution and decimal equivalent only you have to do. Just to calculate the resolution with the help of the reference voltage that will be given, and then transform it into corresponding equivalent analog voltage. Now you can make the comparison here. Clear? Fine. So appo inga vara voltage ipo neenga reduce pannunga, what we are going to get? Let me do it by myself. One second. So 128, wait a minute, 128, so 128 into 5 upon, we should 255. I am getting 2.5, right? I am getting 2.5. So actually inga enak evlo voltage varudhu appadina, case number 1 I am getting 2.5. Now let's compare. 3.5 is greater than 2.5 na? Yes. So the data that we are taking here is exactly correct. அப்போ நீங்க next clock pulse என்ன பண்ணிக்கலாம், ஆல்ரெடி எடுத்த டேட்டாவை அப்படியே எடுத்துக்கிட்டோம், because condition is valid. If input voltage is greater than decimal equivalent, then the condition is valid. நீங்க ஆல்ரெடி எடுத்த டேட்டா கரெக்ட் தான். ஸோ அதே டேட்டாவை எடுத்துக்கிட்டு go to the next bit from the MSB, just to make it as 1. Again continue 1 2 3 4 5 6. This is the next data. Let us consider its equivalent value. அப்போ இதுக்கு உங்களுக்கு equivalent value என்ன வரும்? Its equivalent value is 2 power 7, right? 2 power 7 plus 2 power 6, right? So let us consider the second data. Decimal equivalent is what? 2 power 7 அப்படினா 128, right? 2 power 16 is 64, right? So 128 plus 64, wait a minute, plus 64, I am getting 192, right? So 192 into 5 divided by 255. Again we are transforming it, right? அப்போ நீங்கள் கன்சிடர் பண்ணீங்கன்னா செகண்ட் கேஸில் எனக்கு எவ்வளோ வருதுன்னா 3.76 வருதுங்க. இது கரெக்டா? No, that is wrong actually. This is wrong actually, right? Why? Because the data is, you can accept 3.5 is the maximum voltage from the input side. You cannot transform beyond this voltage. But here I am facing 3.76. Just in place of 128, place 192. Why? This is the decimal equivalent of this one. 2 power 7 into 1 plus 2 power 6 into 1. Rest of data are 0. That will be equal to 192. So 192 into same. Resolution won't be changed. That is 5 by 240, 55 only. So I am getting 3.76. Again, if I will compare these two, condition is invalid. If your data is invalid, once again, what we need to do, again we have to reset the data, right? So the reset the data in the sense, take the previous data, right? Previous data, you can replace 1 by 0, but again 0 ku bala you can replace it by 1. You can replace it by 1, right? So that is the next data. Again, if you find the decimal equivalent for this one, 1 into 2 power 7 plus 1 into 2 power 5. 2 power 5 is 32. 32 plus 128. 128 plus 32. Again, I am getting 160. In place of 192, let me place 160. Then what I am going to get? 160 into 5 by 255, right? So 160 into 5 upon, if I will consider it, divided by 255, I am getting 3.13. Next data will become 3.137. Such that, see that 3.5 is greater than 3.137. So the next data is going to be, right, 101 is correct. Again you can replace. Other data, 0 1 போட்டுக்கிட்டு you can consider rest of 4 zeros. Right? Are you getting me? Correct data இருந்தா அடுத்த டேட்டாவுக்கு நீங்க 1 போட்டுக்கலாம். தப்பான டேட்டா இருந்தா ஆல்ரெடி எடுத்த டேட்டாவை நீங்க என்ன பண்ணணும்? யாருக்கு 1 எடுத்தீங்களோ அதை 0வா செட் பண்ணிட்டு யாருக்கு 0 எடுத்தீங்களோ அதை நீங்க 1ஆ ட்ரான்ஸ்ஃபார்ம் பண்ணணும். This is how we are traveling along with the output of the successive approximation register when the reference voltage will be given to us, right? One second. Yeah. Now in this process, right, what is our output? Actually, see, we know first clock pulse, right? So in the first clock pulse, this is the data that was registering into the circuit, right? 10040, let us consider 8 1 2 3 4 5 6 7 8. First clock la இந்த data தான் enter ஆயிருக்கும், right? Second clock la நமக்கு என்ன data enter ஆச்சு? Actually I was entering along with the 11160 1 2 3 4 5 6, கரெக்ட்டா? இந்த data கூட தான் நம்ம enter ஆகணும். But what happened there? What was happened there? இங்க என்ன ஆச்சு அப்படினா தப்பாயிடுச்சு, இந்த data வந்து தப்பாயிடுச்சு. திரும்பவும் நம்ம counter என்ன ஆச்சு? It has been resetting this one, right? So such that it become 101 and then it is continuous. Clear? அதுக்கப்புறம் என்ன ஆகும்? Next clock pulse we are going to get this data. Right? So what is third clock pulse, what we are going to receive? Now just observe this one. This is the first term that we are receiving, and then in the second case actually we are receiving this one. This is the second clock pulse, that is what I am getting. But while giving the third clock pulse, I have to reset the data, and then you can entering into the next data, such that while entering into the third clock pulse, right? So we are going to get this one as the output. Clear? That's all. I hope things are clear, right? So I'm repeating once again, there are no things to understand. Digital to analog converter output voltage ku formula உங்களுக்கு தெரியும். அந்த formula யூஸ் பண்ணி reference voltage கொடுத்திருக்காங்க அப்படினா just transform this voltage into decimal equivalent. See, I would like to conclude one more thing. In your examination you will face the question in this way only, right? When I was taking the basic operation, I just took the decimal equivalent and just I have run up with the output voltage. I took reference voltage as 1 because I did not take any different values, right? But the thing is, if it is given what I can say, reference voltage will be defined as certain value will be given and bits alla kuduthiranga, you will have to resist the, because this is the exact procedure. Digital la analog converter kulla you may keep, we saw two methods, R2 or ladder irukkalam illa binary weighted resistor irukkalam, right? So adala edha oru method inga kuduthirundana adha actual output enna varum namakku theriyum. Just go ahead with that procedure. அந்த ப்ரொசீஜரை யூஸ் பண்ணிக்கோங்க. பெருசாக நாங்கள் எதுவுமே பண்ணல. நார்மல் ஆப்ரேஷனுக்கு பதிலாக டிஜிட்டல் டு அனலாக் கன்வெர்ட்டர் அவுட்புட் எக்ஸ்பிரஷனை யூஸ் பண்ணி நம்ம ப்ரொசீட் பண்ணியிருக்கோம், ரைட்? அண்ட் கிளியர்லி யூ ஹவ் டு அப்சர்வ். நீங்கள் இப்போ என்ன பண்ணோம் அப்படின்னா, ஃபர்ஸ்ட் கிளாக் கொடுக்கும்போது நமக்கு என்ன டேட்டா வந்தது சார்? தோ தெர் இஸ் நோ பாயிண்ட் ஆஃப் கெட்டிங் கன்ஃபியூஷன். ஃபர்ஸ்ட் கிளாக் ஐ எம் கெட்டிங் 1 2 3 1 2 3 4. திஸ் இஸ் தி ஃபர்ஸ்ட் கிளாக் டேட்டா. First clock, right? And second data நமக்கு என்ன வந்துச்சு அப்படின்னா, actually this data is correct. இதுக்கு நமக்கு output voltage என்ன வந்திருந்தது அப்படின்னா 2.5 we are getting, such that I went up, okay my data is correct. அப்போ நீங்கள் செகண்ட் அடுத்து நீங்கள் MSBல 1 செட் பண்ணிட்டு ரிமைனிங் இருக்க டேட்டாவை அப்படியே கன்சிடர் பண்ணிக்கலாம். ஆல்ரெடி நான் இதுக்கு என்ன கொடுத்துட்டேன் அப்படின்னா செகண்ட் கிளாக் கொடுத்தாச்சு, கொடுத்து டேட்டா வெளியில் வந்துருச்சு. பட் வெளியில் வந்ததுக்கப்புறம் என்ன ஆயிடுச்சு அப்படின்னா டேட்டா வந்து ரீசெட் ஆகணும், பிகாஸ் திஸ் இஸ் ராங் டேட்டா. இது ராங் டேட்டாவாக இருந்ததுன்னா அப்போ தேர்ட் கிளாக் பல்ஸில் என்ன நடக்கும் அப்படின்னா, அகைன் 1 is 1 only, பட் திஸ் 1 will be reset. திரும்ப என்ன பண்ணும் அப்படின்னா கவுண்டர் வந்து டேட்டாஸ் வந்து ரீசெட் பண்ணும். ஆல்ரெடி இருந்த 1 0 மாற்றும், 0 1 மாற்றிட்டு இட் வில் கண்டினியூ இட்ஸ் ஆப்ரேஷன். அப்போ தேர்ட் கிளாக் கொடுக்கும்போது என்ன ஆகும் அப்படின்னா ஆல்ரெடி எக்ஸிஸ்ட் ஆயிருக்க டேட்டாவை அதை ரீசெட் பண்ணிக்கும். இப்போ திரும்பவும் செக் பண்ணி பார்க்கும், ரைட்? ஸோ இப்போ இதை திரும்ப செக் பண்ணி பார்க்கும்போது என்ன ஆகுனா, ஓகே திஸ் டேட்டா கரெக்ட் அப்படின்னா ஓகே ஃபைன். அதுக்கப்புறம் இருக்க 0 1 செட் பண்ணிட்டு இட் வில் கண்டினியூ. திஸ் இஸ் தி ஃபோர்த் கிளாக் பல்ஸ். சப்போஸ் இப்போ இதோட டெசிமல் ஈக்குவலன்ட் கால்குலேட் பண்ணுங்க, இது எவ்வளோ வருதுன்னு பார்த்துருவோம். திஸ் இஸ் 2 power 7 128 ஈக்குவலன்ட் வேல்யூ ப்ளஸ் 2 power 6 கிடையாது, 2 power 5 32 ப்ளஸ் 2 power 4 that is 16. 16 this is 48. 48 this is 68 76 176, right? Yeah. So 128, let me check it by myself. So I'm getting 3.45. 3.45 is acceptable value because which is less than 3.5 only. So அப்போ திரும்ப என்ன பண்ணோம் அப்படின்னா அடுத்து நீங்கள் 5th கிளாக் அப்ளை பண்ணும்போது ஆல்ரெடி நம்ம எடுத்த டேட்டா கரெக்ட் தான். ஸோ go to the next data, it will continue like this. Clear? This is for 5th clock pulse. Now see there, question is what? Third clock pulse உங்களோட ஆன்சர் என்ன அப்படின்னு மட்டும் தானே கேட்டிருந்தாங்க. Yes, this is the third clock pulse answer. So my answer is 101040. So 101040. This is the correct answer. Just observe this operation with the given data that I am giving now. நம்ம ஆல்ரெடி பார்த்தது basic. I am repeating, that is basic அப்படின்னா ஒரு டேட்டா டிஜிட்டல் இருக்குது, அது அப்படியே டெசிமல் ஈக்குவலன்ட் கன்வெர்ட் ஆகும்போது how your successive approximation will work. That is what we saw, right? But with the standard digital to analog converter actually எப்படி work பண்ணும்? This is the output voltage expression for digital what I can say digital to analog converter. With this we are going about, this is the exact operation, right? Reference voltage will be given just to proceed with this one. You will be tested with this type of questions only, right? Yeah, of course I told you now many clock pulse full கொடுக்க மாட்டாங்க, 2 or 3 clock pulse தான் உங்களுக்கு கேட்பாங்க for time being, right? You can easily post your answer, right? Okay, now the thing that you have to remember is first data வந்து நீங்க கொடுக்கும்போது கரெக்டான டேட்டாவா இருந்தது அப்படின்னா see there, first நீங்க clock கொடுத்த உடனே டேட்டா என்டர் ஆகுது, செகண்ட் clock கொடுக்கும்போது டேட்டா உள்ள வருது, but that is not correct data, that is wrong data. அப்போ நீங்க ரீசெட் பண்ணும்போது again you are applying one more clock. கவுண்டர் என்ன பண்ணா தேர்ட் clock கொடுக்கும்போது it will change the data. Again it will check same operation இது perform பண்ணும், right? it will be continuous. first clockல enter ஆன டேட்டாவோட டெசிமல் ஈக்குவலன்ட் வெளியில வருதா, கம்பேரிசன் இங்க நடக்குது. திரும்பவும் செகண்ட் clock கொடுக்குது, செகண்ட் clock கொடுக்கும்போது டேட்டா வந்து சேஞ்ச் ஆகுது, ரைட்? என்னவா சேஞ்ச் ஆகும்னா 1100 இந்த மாதிரி சேஞ்ச் ஆகும். திரும்பவும் இங்க வெளியில கம்பேரிசன் நடக்கும், ராங் செட், ரைட்? இன்வாலிட் ரிலேஷன் வந்தது அப்படின்னா அகைன் கவுண்டர் என்ன பண்ணும் அப்படின்னா அகைன் we are giving one more clock to change the bits. பட் இந்த கேஸ்ல என்ன நடக்கும்னா அவுட்புட் வந்து 0 வரும். அப்ப 0 வந்துச்சுன்னா this output is going to be 0. இந்த இடத்துல 0 வந்துச்சுன்னா successive approximation rate என்ன பண்ணும் அப்படின்னா அப்ப லாஸ்ட் கேஸ்ல நான் எடுத்தது தப்பான டேட்டா போல, so I am getting 0 here அப்படின்றது அது தெரியும். திரும்ப அது என்ன பண்ணும் அப்படின்னா நெக்ஸ்ட் கிளாக் அப்ளை பண்ணும்போது automatically it will change the data. திரும்ப it will continuous, right? That operation will be continuous. That's all. Clear? I hope things are clear now. Let me select if I'll find new questions. No, there are no questions beyond this, all are same model, it's over, right? So this is all about converters. I hope things are very clear, right? Please rewatch this video, that is this question alone once again, right? Clearly understand, right? I have not given any blab story, right? That operation will be slightly different, I know, because here I went up with the exact output, right, of the digital to analog converter, right? Because in your examination they will test you, right, with this model only. Just should try to keep it in your mind, right? That's all. This is all about converter circuits. It is completely over. There is one more small topic that we need to discuss about, that is the basics of the logic families, right? Yeah, so now we need to discuss about the logic families, right? So today evening I will complete that one also. That is a small topic only. We will compare here itself, we will discuss the basics. Tomorrow, that is in the next session, we will start our next subject, that is measurements, right? I hope you all understand. If you have any doubts, you can ask in our group. With this, let's wind up the class. Thank you all.